Hello, I'm going to be explaining the methods of integration. Those are substitution, integration by parts, partial fractions, and trigonometric substitution. And it's important to keep in mind that we use all of these methods to obtain an integral that we can directly integrate. So essentially, we're simplifying an integral. First is integration by substitution. So we have to choose an expression that will be substituted for the variable u. And the goal of this is to cancel out the x's in the original expression f of x, so that we're left with only an integrand that has the variable u. So for example, we could choose an expression whose derivative is already in f of x. Next, we'll calculate the derivative, du over dx. And we can rearrange for dx because you'll see that we have to substitute this back into the original equation, integral of f of x dx, right here. So we substitute u in dx. Then we do the integral with the integral methods we know. And at the end, we undo the substitution by replacing u with g of x. First, let's look at this example, 2x plus 1 times e to the power of x squared plus x. You'll notice that the derivative of x squared plus x is 2x plus 1. So once we substitute this for dx, we can cancel out 2x plus 1, and we're left with the integral of e to the u. Now this is an integral we know. And once we've done the integral, we can unsubstitute. So we undo the substitution by putting x squared plus x instead of u. Next, we have integration by parts. So you'll notice that there's f prime of x and there's g of x. So the first step is to identify which is which. And keeping in mind that the goal is to obtain an integral that's simpler to integrate than the one we had before. So for this, we're going to have to choose a g of x that becomes simpler when we derive it. So for example, ln of something, a power of x, a polynomial, or even just x. Then we will find the integral of f prime of x to get f of x, and the derivative of g of x, g prime of x, to apply in the integration by parts formula. And then we just simply calculate this and we integrate. So an example of this is x ln of x. So I'm going to choose ln of x as my g, so that when I derive it, it gives an expression that's simpler. Because I couldn't choose it as f prime of x, I don't know how to do the integral of ln of x. Next, once we apply the integration by parts formula, we get this expression, and we see that the x squared cancels out with the x here, and then we can combine the two expressions on the left. We're left with the integral of x. So when we calculate this, this is what it gives, and then we can simplify everything down. Partial fractions deal with an f of x that has two factors on its denominator. So if it hasn't already been done, we need to factorize the denominator into two factors. Then we assign coefficients, a and b, to each of these factors. We multiply both sides by the denominator. So factor 1 times factor 2, if we multiply with a, factor 1 will cancel out, so we're left with a times factor 2. We do the same for b. Then we isolate for a by choosing a value of x so that factor 1 is equal to 0. So that just leaves us with a times factor 2 equals the numerator of f of x. And then we do the same for b, so that factor 2 is equal to 0. We replace this f of x with our newly found values of a and b in the original integrand, like this, and we integrate both expressions. So this is much simpler with examples. Let's look at that. For this example, the denominator is not factorized, so we're going to go ahead and do that. Factor 1 will be x plus 2, and factor 2 will be x minus 2. Then we multiply both sides by the denominator, which leaves us with this expression. And to isolate for a, we'll put x is equal to minus 2, so that we're left with 8 equals minus 4a, so a is equal to minus 2. We do the same process for b, except this time we use x is equal to 2. And that leaves us with the integral of minus 2 over the first factor, plus the integral of 2 over the second factor. So to integrate this, we're going to do a u substitution. In this case, we're going to have u is equal to x plus 2 here. So that leaves us with minus 2 times the integral of du over u, which just leaves us with minus 2 ln of u. And here, we're going to use u prime, and u prime is going to be equal to the second factor, x minus 2. And here it gives us 2 times ln of u prime, in absolute value, of course. So the final answer is over here.
Just to clarify, I did use u prime in the last example, but I used it as a variable different from u. I didn't mean the derivative of u, but rather just any other variable than u. It could have been v, so I wanted to make sure that was clear.
For trigonometric substitution, we substitute x for a trig function of t so that we can then simplify the integral with trig identities. So when we have a squared minus b squared x squared, we'll substitute for a over b sine t. And if we bring it into the original expression, it's going to give a squared minus a squared sine squared t. So we can use the trig identity cos squared equals 1 minus sine squared and factor out a so that we are left with a squared cos squared t. And we can then do dx over dt because it's a function of t, and then isolate for dx so that we'll be able to substitute dx into the original integral. Then for a squared plus b squared x squared, we can substitute for a over b tan t. So it's going to look like this once we substitute into the original expression. And using the identity x squared equals 1 minus tan squared, we can simplify it down to this. So we do the same process, and then we can integrate and undo the substitution for t once we've integrated. So for this, we have to isolate for t in the original substitution. So t is going to be arcsine of b over ax. And we'll do the same process here. So the original substitution is with tan this time. So if we isolate for t, we get arctan of b over ax. So the general process for trig substitution consists of substituting x for a over b either sine or tan of t. Then we calculate dx over dt and isolate for dx. We integrate it as a function of t, and then we undo the substitution for x by isolating t in this original substitution. So let's illustrate this with the following example. Notice that this is a form a squared minus b squared x squared. So we'll substitute for x equals a over b sine t, which gives 5 over 2. Because a squared is 25, so a is 5, and b squared is 4, so b is 2. Now, dx over dt will give 5 over 2 cos of t, and that means that dx will be 5 over 2 cos of t times dt. So after the substitution, as we know, it will give a squared cos squared of t, which means here that it will give 25 times cos squared of t, and dx we can substitute for as we did over here. And once we simplify all of that out, we're going to have square root of 25 is just 5, so this cancels out. 1 over 2 we can bring outside over here. And then the square root of cos squared of t is just cos of t, so that's going to cancel out here. So we have 1/2 integral of dt, which means that we have 1/2 times t plus c. And in the original substitution, if we isolate for t, we get t is equal to arcsine of 2 over 5x. So that's what we're going to do. We're going to undo the substitution for t like this, and this is our final answer. Here is my works cited. So I used inspiration from the textbook and from the class notes as well.
This first number is a u substitution, but I have to prepare it using the trig identity cos squared of x, well in this case x to the 6, is equal to 1 minus sine squared of x to the 6. So because I have cos cubed times sine squared, I divide it into cos of x to the 6 times cos squared of x to the 6 to use this identity. So I have, after using it, x to the 5 times cos of x to the 6 times 1 minus sine squared x to the 6 times sine squared x to the 6 dx. So the integral of all of this. And after that, I can substitute for u equals sine x to the 6, knowing that its derivative will have cos x to the 6, which I can cancel out with the cos x to the 6 over here. So u equals sine x to the 6, which means that du over dx is 6 times x to the 5 times cos of x to the 6, and then I isolate for dx. So once I substitute all of that in, I can cancel out cos of x to the 6 and cos of x to the 6 here. And I can also cancel out the x to the 5s. And I bring out the 6 because it's 1 over 6. So here I'm left with the integral of u squared minus u to the 4 du. So I can do each of those separately. The integral of u squared is u to the 3 over 3, and then I have a negative here, so I have minus the integral of u to the 4 du, which is just minus u to the 5 over 5. And I can't forget my 1 over 6 here, so I have to multiply both of these by 1 over 6 to get u cubed over 18 minus u to the 5 over 30. And then I can undo the substitution for u that I did over here, and I'm left with sine cubed of x to the 6 over 18 minus sine to the 5 of x to the 6 over 30. And I can't forget my plus c, which actually I can add here as well because I did the integral. So there it is. In this example, I'm going to combine u substitution and partial fractions. So first of all, 1 over e to the x minus e to the minus x, I can't do anything with that. So I'm going to rewrite it by multiplying the denominator and the numerator by e to the x. Pretty simple. So that gives me e to the x over e to the x squared minus 1. And after that, I can use substitute for e to the x. So du over dx is also e to the x, which means that dx is du over e to the x. And once I figured all of that out, I can cross over this e to the x and this e to the x. They cancel out. And I'm left with 1 over u squared minus 1 du. And you'll notice that this is a partial fractions. So I can factorize the denominator like this. So I have u minus 1 and u plus 1 as my two factors. So I'll assign them a and b, a coefficient. And if I want to isolate for a and b, as previously mentioned, I have to multiply by the denominator. So I'm going to do that. And then I'm left with this expression. So if I use u is equal to 1, I'm going to have 1 is equal to 1 plus 1, so 2 times a, plus 1 minus 1, so 0 times b. So 1 equal to a, and a is equal to 1 half. Same process for b, except this time I'm using u equals minus 1, and I'm going to get b is equal to minus 1 half. So that leaves me with this integral, but in this form. So for this integral, I'm going to take out the 1 half, and I have the integral of du over u minus 1. So I'm going to substitute another time, and this time I'm going to use the letter v to distinguish from u. So v is going to be u minus 1, which means dv over du is 1, so dv is equal to du. And then I have v to the minus 1, which is just ln of the absolute value of v. So 1 half times ln of the absolute value of v plus c. And it's similar for this integral. Instead, I'm going to use w to distinguish from v and from u. And w is going to be equal to u plus 1. So I have dw is equal to du, and the same process as in the other integral, but this time it's minus 1 half times ln of the absolute value of u plus 1, plus c, obviously. And so I can combine both of these and undo the substitution for u. So u is equal to e to the x. I bring this substitution all the way down here, and then I undo the substitution. So I have ln of absolute value of e to the x minus 1 over 2, minus ln of absolute value of e to the x plus 1 over 2, and then plus rc. This next integral is a simple trig substitution. So we have this original expression, 1 over square root of 25 minus 81x squared. So we can immediately identify that it is a form a squared minus b squared x squared. And here a squared is 25, b squared is 81, and obviously we have x squared. So we know that in this case we have to substitute for x is equal to a over b sine of t. And in this case, a is the square root of 25, so 5, and b is the square root of 81, so 9. And that leaves us with dx over dt is equal to 5 over 9 cos of t, so dx is going to be 5 over 9 cos of t times dt. And now we can substitute all of this in this equation. So we know that in this form, we're going to be left with a squared cos squared of t. So in this case, a squared is 25 and cos squared of t is here. And then we also substitute for dx this expression over here. And we can immediately cancel out several things. So the square root of 25 is 5, so we can cancel out 5 and 5. And the square root of cos squared is just cos, so we can cancel out cos and cos. So that leaves us with 1 over 9 dt, and we can bring the 1 over 9 outside of the integral. so that we're left with the integral of dt, which is just t. And obviously we multiply t by 1 over 9, so we have t over 9 plus c. That's the integral. Now, we have to go isolate for t in the original substitution we did, and we do this very simply. So x is equal to the substitution, we divide by 5 over 9, and then we do the arcsine of both sides. So we're going to bring this t value into our final answer over here. So arcsine of 9 over 5x over 9 plus c. This number is a u substitution where we have to notice that substituting for u is going to cancel out this u over here. So if I want to substitute for square root of x, I'm going to have u is equal to x to the 1/2, and I notice that the derivative of x to the 1/2 is 1/2 times x to the minus 1/2, so 1 over 2 square root of x. And if I isolate for dx, I'm going to get 2 times square root of x times du. And I know that this will be able to cancel out the square root of x on the bottom, which is why I choose u, because if I just do cos of u over u, this will not work, but I can keep my square root of x on the bottom and then cancel out my 2 square roots of x. And so I can cancel this out over here once I've substituted everything, and I can bring my 2 out of the integral. So I'm left with 2 times the integral of cos of u du, which is 2 times sine of u, and I have my plus c. So I can then undo my substitution. I had u is equal to 1x to the 1/2, so square root of x. I can undo the substitution, and it's as simple as that. This number is a very simple u substitution. So I have to notice that arctan of x has its derivative as 1 over 1 plus x squared. So this part of its derivative is already in the expression f of x here. So when I isolate for dx, it's going to end up on the numerator. And since 1 plus x squared is on the denominator of f of x, they're going to cancel out. So I will substitute for u over u equals arctan of x, which is going to give me dx equals this, as I mentioned. So I'm going to be able to cancel out 1 plus x squared, and it's going to leave me with the integral of u to the 4 du, and that's just u to the 5 over 5 plus c, and then I can undo the substitution for arctan of x. So it's going to be arctan of x to the 5 over 5 plus c. Finally, there's this simple integration with partial fractions. So we have this expression, which we can then divide into a over x plus 5, which is our first factor, and b over x minus 2, our second factor. So then we multiply by the denominator to get x minus 9 equals x minus 2a plus x plus 5b. And then we want to isolate for a and b. So we're going to put x equal to minus 5 to cancel out the factor on b. So we're going to have minus 5 minus 9 equals minus 5 minus 2a. And then this factor is going to be 0. So we have minus 14 equals minus 7a, so a is equal to 2. And we do the same process to isolate for b. This time we're going to put x is equal to 2 to cancel out the factor in front of a. So we have 2 minus 9 equals 2 minus 2a, so there's no a, and 2 plus 5b. So minus 7 equals 7b, b is equal to minus 1. Now that we have a and b, we can take this original equation here and use the coefficients that we found. So we're going to have 2, which is a, over its factor x plus 5 dx, so this integral, plus the integral of minus 1 over x minus 2 dx, which is the same as minus the integral of 1 over x minus 2 dx. And we can then do a u substitution for, in this case, x plus 5. So du is going to be equal to dx. And that leaves us with du over u, which is just ln of the absolute value of u. So we have 2 times ln of the absolute value of x plus 5 because we had a 2 in front. So we bring the 2 out of the integral. And the same is true for this integral. I'm going to use v this time to distinguish it from u. So v is going to be x minus 2, which means that dv is equal to dx. And then I bring the minus out of the integral, and it leaves me with minus ln of the absolute value of v. So ln of the absolute value of x minus 2 plus c. This is the bonus number I did just to show how to do the integration by parts, so you don't have to watch it. But essentially, I substituted for u here, knowing that the derivative of 9 sine x would be cos x, well, 9 cos x, so it can cancel out with the cos x that's over here. And that means that du over dx is 9 cos x, which means dx is du over 9 cos x. So I substitute all of that. I cancel out the cos of x, and I bring out the 9 over here. So I'm left with the integral of ln of u. I need to do integration by parts. So I choose f prime to be 1, so f is u, and g to be ln of u, obviously, which means that g prime is 1 over u. So with the integration by parts formula, I can do u times ln of u minus the integral of u times 1 over u, which means the integral of just du, and that gives me u. Now I have u ln of u minus u, so I can undo the substitution, and I have to keep in mind that I had this 1 over 9 here, so I bring it down, I multiply both terms by 1 over 9, and I undo the substitution for u, so I'm left with just sine of x times ln of 9 sine x, minus sine x, because the 9 here and the 9 here cancel out with the 1 over 9. Then I do the upper and lower bound, so 0.6 and 0.4 for this expression, and I'm left with this long equation. So that's it.